All right, well, we're going to start out today by looking at balancing oxidation reduction reactions. So we're going to go ahead and start with this slideshow. And starting this, hopefully this will begin here. And this is something that I came across in 2001 at an AP Teachers Conference. So this is a way I've been teaching it for about 20 years. I've perfected it a little bit and simplified it a little bit since then. Dr. John Gelder and Valerie Ferguson are the ones that initially introduced this to me, but it also appears in an article in a journal of the chemical education, and the information for that is there. Now, for those of you who are looking at balancing reactions, you don't need to go up and look up the Journal of JChem Ed. You're welcome to do so if you want to. The information is right there. Okay. Now, the journal article lists steps to balancing oxidation reduction reactions. And I've included the journal's list of them right here. And notice it's got 13 steps, and some of them are A and B and A, B, and C. So with that, I thought, well, okay, so all this is really good. They're going into really detail of what you need to do, but I like to simplify it a little bit. You know, I overly simplify things. In order to start simplifying it, we need to remember a couple things. First of all, what's an ion? Now, I know you're thinking, oh, an eye is on a face, right? No, that's not what we're talking about when we say what is an ion. An ion is something that has lost or gained an electron. For example, if I take iron, it can lose 2 electrons and become iron 2. Now, what's interesting is that same iron 2 ion can also gain 2 electrons back and become iron, or it can lose another electron and become iron 3. So anything can lose or gain an electrons. It doesn't have to be an atom. Any ion can lose or gain an electrons. And we're going to need to go back through and remember our rules for assigning oxidation numbers. Now, that's not what this presentation is about. So if you need help with that, you're going to have to go back into your textbook and look at the oxidation number rules. Okay. You do need to remember that electrons that are lost is oxidation, and electrons that are gained is reduction. Leo says grr, grr. Okay, so let's look at the steps to balancing oxidation reduction reactions in the overly simplified version. Okay, first of all, assign oxidation numbers to each and every element. Now you need to, after that, determine which elements undergo a change in oxidation number. There's always going to be an oxidation and a reduction. Now, there's some really complicated ones in which more than 2 elements undergo a change in oxidation number. We're not going to look at those, although those do exist. Okay, you'll need to write the half reactions. Now, a half reaction is where we write the element that's undergoing oxidation, including the electrons that are moving. So if it's oxidation, the electrons are lost. The electrons are going to be on the right side of the equation. If it's gaining electrons, we're adding electrons to it. Means the electrons are on the left side of the equation. And it might help if you remember the electron charge is a -1. Okay. Then we need to balance the electrons. We're going to find the least common multiple. And now I know you're thinking, least common multiple. I remember we covered things like least common multiple and greatest factor and all that stuff. And I never used that. Well, here is your chance. You get to use the least common multiple. Okay. You're going to then determine the charge on each side of the equation, and then add the charged species to get a charge balance. So you have to figure out what the charge is on the left side of the equation, what the charge is on the right side of the equation. Now, in this case, you might think, now, oxidation number and charge, are they the same thing? No, they are not. And that's why we always write the oxidation number with the sign first and the charge with the number first. Now, in order to balance it, we're going to add a charged species. In the case of acidic, that charged species is going to be H3O+. You can also do this with H+, although I'm going to teach it with hydronium ion and not just the hydrogen ion. If you learned it with the hydrogen ion and want to use that, that's fine. For basic solutions, we're going to add hydroxide. Okay? We'll then balance the hydrogens by adding water to whichever side needs them. Once you have done this, you have a charge balance, you have a hydrogen balance, the oxygen should be balanced. If not, a mistake has been made. Okay, So let's take a look at an example. We're going to keep it basic here. Okay, so not only is that a joke, we're going to take a look at this equation, which reacts in a basic solution. Permanganate plus bisulfite gives us the manganese dioxide plus sulfate. Okay, the reaction is shown below. So where do we need to start? Assign oxidation numbers. Okay, so let's do that. Now, I'm not going to go through these right now one by one. If you have questions, feel free to shoot me an email or ask about that. But manganese has a +7, oxygen a -2, hydrogen +1, sulfur +4, oxygen -2, +4 for the manganese here, -2, +6 for the sulfur here, and -2 for the oxygen there. Now, as we do this, we've completed listing them all. We need to look for the two elements that change oxidation numbers. In this case, manganese, which goes from a +7 here to a +4, and sulfur, which goes from a +4 to a +6. And we're going to remember the electron has a charge of -1. If I want to go from a +7 to a +4, I have to add 3 -1s. It's gaining electrons. Grr. Okay. So, writing our half reactions, here is our manganese half reaction. Notice I have one manganese here and one manganese here. That has to be balanced. If I had 2 on one side and 1 on the other, I would have to balance that element. I don't have to worry about the other elements. I don't have to worry about the oxygens at this point. We'll come back to that later. Okay, so here's our reduction. Here is our oxidation half reaction, +4 to a +6 plus the 2 electrons. And then we're going to balance the electrons gained and lost by finding the least common multiple. The least common multiple of the 3 electrons that I have here and the 2 electrons I have here. Then I need to balance the electrons. I'm going to need to have a least common multiple of 6. That means I need to multiply this equation by 2, this equation by 3, and then I'm going to put them into my overall equation up here. So see, I take my original equation, 2 manganeses here, 3 sulfurs here, 3 sulfurs here, and we have it. Now, we're not done yet, but we have our elements that are oxidized and reduced balanced. We don't have our charges balanced. In any reaction, I have to have the same amount of charge on the left side and the right side. Otherwise, electrons are lost or gained somewhere, and we can't have that. That's not really balanced. So we need to pay attention to the charge here. Over here, if I look at it, I have 2 permanganates, which have a -1 charge, and 3 bisulfites, which have a -1 charge. This gives me my total of -5 here. And the manganese dioxide doesn't have a charge, so I can take 2 times 0, I still get 0. And I have 3 sulfates. So if I look at it, this side has a -5, this has a -6. Because it's basic, I'm going to add hydroxide, okay? And it's negative. I have a -5 and a -6. I need to add a hydroxide to my left side. Oh, right there. Okay. So now I have a charge balance on both sides. This one was a fairly simple one. I only needed to add 1. You can add, sometimes 2, sometimes 4. It might even be like 24 or something like that. The large numbers should not scare you off unless all of these are really small numbers, okay? Now, this is not balanced. We have a charge balance. We have a balance of the elements undergoing an oxidation and reduction, but the whole thing is not balanced yet. We need to add water to balance the hydrogens. Now notice on this side I have 3 hydrogens here and 1 hydrogen here. That's a total of 4 hydrogens. 4 hydrogens, that means I need to add 2 waters to the other side. Sometimes you'll have hydrogens on both sides and just need to find out what the difference is. Now when I do this, I add my 2 waters to the right side. The oxygen should be balanced. Now I can go through that. 2 times 4, 8 oxygens here. 3 times 3, 9 oxygens here, 1 here, I have 8 here, 12 here, and 2 here, or 18 oxygens on each side, and I have an overall balanced equation. Looks fairly simple. Although remember that even me explaining this simple one took about 5 minutes. This is not going to be something you're going to be able to sit down, look at, and just write things out. It's going to take a little bit of time to do these. And go ahead and spend the time doing these and practicing some of these. Now, sometimes we're going to need to balance just a half reaction. And some of you may have used a bridge method where it just lists the two elements and the other two elements and using a charge balance. You can do the same thing with that if you learned another way. If you were taught by somebody who says you have to balance the entire half reaction before you combine them together, you can do that. There are times where we're going to have to do that. So I'm going to show you that. A half reaction is going to be the same thing. Now, again, this particular one is an oxidation. I go from manganese, which is a +7, to manganese, which is a +4. So I gain 3 electrons here. When I look at my charges over here, I have a -1 charge and 3 negatives here. Remember, the electron has a charge. Now this side, there's nothing here, okay? So I have a -4 here and a 0 here. Because this was in a basic solution, I need to add 4 hydroxides to the right, giving me a -4 overall. I now have 4 hydrogens here, but I don't have any over here, so that means I need to add 2 waters over here. And when I do this, 4, 5, 6, I've got 2 and 4 or 6 oxygens. It is balanced. Now it's time for you to work on some of these on your own.